When we read the outputs of modern language models, it is easy to assume they possess an inherent grasp of human communication. They write poetry, generate complex code, and craft essays with a fluency that feels as if every rule is locked perfectly into place. But here is the paradox behind that fluency. The engineers who build these systems do not program a single grammatical rule, part of speech, or dictionary definition into them. Every one of these models begins its life as a completely blank slate of code. At day zero, the system has no knowledge of what human words mean, let alone how to string them together. So if an AI is never explicitly taught the rules of language, what exact mechanism allows it to learn fluency? Fluency emerges from a hidden mechanical process, an engine that generates complex communication entirely from scratch. The entire objective of this engine is tied to a single task called language modeling. Stripped down to its core, language modeling is the act of predicting the very next token in a sequence. To master this, the machine relies on supervised learning. It needs to be fed an input prompt, followed immediately by the correct target answer, so it can check its work. Gathering enough of these inputs and targets manually would take centuries. Instead, engineers use a trick to automatically extract them from text that already exists. Consider a simple sentence. Jide was hungry, so she went looking for food. We can isolate the first two words, Jide was, and define them as our input group. That makes the very next word, hungry, the target the model needs to predict. Shifting our focus just one word to the right, Jide was hungry becomes the new input, and so becomes the new target. By moving this sliding window down the sentence, a single string of text is sliced into 8 distinct training examples. When you apply this same sliding window to vast archives of internet text, you instantly generate the millions of test questions required for training. This automated data slicing provides the fuel for our blank slate model, creating an endless supply of questions and answers. This flowchart illustrates the architecture of a transformer model's training loop. It shows how the AI processes training data through a continuous 3-step cycle. Step 1 is the predict phase. The model takes in the input sequence, Jide was, and calculates its best guess for the next word. Because the model starts completely untrained, its first guess is highly inaccurate. Here, it assigns a high probability to the word bottle, entirely missing the actual target. Next comes the compare phase. The system takes the model's flawed output and measures it against the correct target hidden in the training data. This measurement generates a vital metric called loss, a numerical score representing how far off the prediction was from the true answer. Guessing bottle instead of hungry triggers a massive penalty, resulting in a very high loss score. This high loss score triggers the third step, the adjust phase. The system immediately fires an automated correction signal backward through the loop. As the model receives this signal, it slightly tweaks its internal parameters. The next time it sees Jide was, the math will favor words like hungry or tired, driving that loss score down. Learning is the mechanical optimization of guessing, checking the loss, and adjusting the math. Now take that simple loop and zoom out. This sequence of predicting, comparing, and adjusting is executed millions of times a second across billions of text examples. The entire architecture is locked in a mathematical game, driven by a quest to drive the loss score as close to zero as possible. By constantly adjusting to avoid penalties, the model identifies the deep statistical patterns that hold language together. As the loss score falls, the system effectively maps the structural relationships between words. It absorbs the complexities of grammar and meaning, not by learning rules, but by finding the mathematical path of least resistance through the data. Machine understanding is the byproduct of a relentless feedback loop, repeated across the massive libraries of digitized human text.